Okay, so let's get started. Thank you all for being here. I'm going to talk today about code deobfuscation and intertwining of dynamic, static, and symbolic approaches for deobfuscation. Okay, so who am I? I'm Robin David. I'm still a PhD student at the Atomic Energy Commission in France. I'm working with Sébastien Bardin, which is a full-time researcher. We're basically working in the software safety and security lab, which is primarily doing safety for critical embedded systems. It's known for its platform for analyzing C code, but I'm part of the small team that is working on binary for security. Okay, so what's the context? What's the goal? So the point is there is a lot of malware in the wild. Some of them are obfuscated. So we'd like to address them and to get rid of the obfuscation in order to perform some more in-depth analysis. So the first thing is trying to locate obfuscation if there is any, and in the second step, trying to remove it if possible. And all that, the goal is to recover some kind of high-level view of the program, which is usually the control flow graph. The challenges, static, dynamic, and symbolic approaches used alone are sometimes not enough for addressing binaries that are obfuscated with different obfuscations. And obviously, we have some scalability and robustness issues when dealing with such code. Our proposal is first a new symbolic methods for addressing infeasibility-based problems. I'm going to talk about it just after that. And we propose a combinations handling multiple kinds of obfuscations by mixing different approaches. What we have achieved so far is a set of tools for analyzing binaries, some detection algorithms for several obfuscations, and I will show a great example on external malware. Okay, so the long-term objective is to use a dynamic disassembly, which is meant to be safe because instructions decoded have been executed. So we have a subset of the program that are sure to be executable. And we'd like to improve it with static disassembly, but making the static disassembly more smart, if we can say, by guiding it with symbolic execution and obfuscation-related information. So what's the agenda today? I'm going to do some quick recall about disassembling and dynamic symbolic executions. Then I will present our two proposals. Then I will just talk rapidly of the Binsec platform that we've been working on for the past few years. And then I will move on to the two case studies. The first is on several packers, and the last is on external. Okay, so what's like to disassemble obfuscated code? The idea is to recover some usable representation of the program, getting rid of everything that is useless into the program. Okay, so yeah. And this is an essential task to perform before any in-depth analysis to understand what the program is really doing. Okay, so the disassembly process, as a quick recall, it can be divided into 3 steps. The first step is the code discovery. So finding into the big block of bytes, what's code, what's data into the program, into the sections. It implies to deal with instructions overlapping. For instance, on x86, the same byte can be shared between 2 different instructions, depending on where you start decoding. So that's the first challenge while disassembling. The second step is the control flow graph reconstructions. So basically creating the nodes and edges to encode the flow of the program. So it implies to deal with indirect control flow, like dynamic jumps and things like this, functions that are never returning, and yeah. And the last step is the partitioning namely trying to create some segmentation into the control flow graph to create the different functions in order to make it more visible and usable for a user point of view. So trying to recovering the functions is kind of difficult because functions can share some parts of their code that they might not be contiguous into the binary. It also implies to deal with tail calls. It's when you call a function by making a single jump. Okay, obfuscation, the broad definition of it is any mean that aims at slowing down the disassembly and the analysis process of a program, either for a human or an automated algorithm. So there's plenty of obfuscation used so far, and I'm not going to talk about all of them, but what you can identify into them is that there is, in the general sense, two kinds of obfuscation. The obfuscations that are more targeting the control of the program, hiding the edges in the graph, and the obfuscation that are targeting the data of the program, like ciphering strings, hiding the constants, or hiding any valuable assets into the program in order to prevent signatures or things like this. So we can, there as a control obfuscation, there is CFG flattening, jump encoding, virtual machines, and so on. And what we can see is that this obfuscation also have an impact on the analysis that you can perform on it. As an example, the last obfuscation is the obfuscation using signal on exceptions. And this is typically the kind of obfuscation that we cannot handle in a static way because we cannot know when an exception is going to be raised and things like this. So the obfuscation have an impact on the kind of analysis we can perform on it. And I'm going to talk about two of them today, so that I will present some detection algorithm. The first one is opaque predicates. An opaque predicates is typically a predicate that is always true or always false, but this property is difficult to deduce just by looking at the predicates. You have an example on the right. Here, regardless of the values that can be taken by X or Y, this predicate will always be true. So below you have the assembly of this predicate, and you basically have one of the two branches that is dead. So the question is, okay, why doing this? The answer is that it allows to grow artificially the size of the code by hiding some dead code in the dead branches. And by the way, drowning the genuine code into it. So you can use whatever is invariant into your program to encode opaque predicates. It can be arithmetic, like here. It can be some invariant on your data structure. It could be pointer aliasing, concurrency, and things like this. So we are going to deal with that obfuscation today. And the second obfuscation is the call stack tampering. The call stack tampering is basically the mean of violating the compilation scheme, saying that a ret instruction is always returning to the caller. And because a ret instruction is basically just a jump on the top value on the stack, it depends at runtime what's on the stack at this moment to know where you're going to jump. And you have an example on the right. So this snippet of code is basically the call will push the address of the pop on the stack. The pop will pop its own address. It will then increment it in the head, push it back again on the stack, and the return instruction is basically going to jump 1 byte further after the ret instruction. So that static disassembly would stop disassembling at the ret instruction, not seeing that the payload is really located after. So that's the kind of tricks that are kind of annoying when you want to disassemble an obfuscated program. Okay, the obfuscation, it's basically, we would like it to be the full reverting of the obfuscating transformations, but sometimes, often it's impossible to do the reverse operations because we are losing informations in the obfuscation path. So we consider the obfuscation the fact of simplifying the code in order to facilitate further analysis. Okay, so a quick recall about disassembly. We consider correct a disassembly if it only disassemble genuine executable instructions. So dead instructions should not be disassembled. And we call a disassembly complete if it managed to disassemble all the instruction. So what we basically have is, with a static approach, you're meant to disassemble the whole program, but you can be fooled into disassembling some dead data bytes or dead branches, and you're basically blocked by all the dynamic jump, here with the jump PAX, for instance. So the analysis do scale, but it's not robust to many obfuscation like self-modification and so on. On the other hand, dynamic disassembly will disassemble a subset of the program, but we are sure it to be executable. And the main advantage of dynamic is that it's robust to usually self-modification and this kind of obfuscation. The shortcoming of this method is that it's dependent on the input. So that in theory, if you want to cover the whole program, you have to provide all the possible inputs to your program. And this is where dynamic symbolic execution comes in, which is also known as concolic execution. So symbolic execution is basically the mean of simulating the program using symbolic values rather than constant values in order to obtain some relationship on the path. So as an example, you have this small snippet of code where there is two nested if, and I would like to know what are the conditions allowing to reach the print instructions. So in the middle, we have basically the graph of the functions. And in order to reach the print OK, you have H that should be less than 10, and it also should be greater than B. So that gives us some relationship on the path, and that leads to the given formula, which is A less than 10 and A greater than B. And a solution for that is A equal 5 and, for instance, B equal 1. Usually the last step, we hand it to like off-the-shelf SMT solver. And going dynamic, so dynamic symbolic execution is the mean of working on the dynamic path. So the first pass, you don't choose it. You just run your program and you obtain a path of execution and you run at the top of it. So the question is for obfuscation, why using dynamic symbolic execution? And an answer for this question is, first, obfuscation usually alter the syntax of the program, breaking the nodes, edges of the graph, but you should keep the semantic of the program because you want your program to still do what it's meant to do after obfuscation. And by the way, DSE allows to find new paths. Like in the previous example, with A and B, we would have the satisfying inputs for the two parameters of the functions to get into that path. So that's a valuable analysis in our case. A more complicated example. So let's consider that we have a switch with three cases, the assembly obtained, and what we have obtained with dynamic execution. So we obtain a piece of the control flow graph. And if we want, for instance, to reach the case C, which is meant to be 2, we get that path and we obtain the relationship on that path in order to take this path into the program. So it allows us to generate inputs for covering path, but as you can notice here, we have missed one of the target of the jump PAX of the switch. So we can basically ask, okay, what could be the values for EAX at that point of the program so that you can maybe find new jump targets. So it basically gives the given formula. You want EAX to be different from 0 and 2. And the solution for that is 1, because we have missed one of the nodes. So that's the main advantage of using dynamic symbolic execution in theory. So going dynamic have the advantage of having a feasible path. So we are sure it to be feasible into the program. We can potentially generate new inputs, and it allows to thwart basic tricks of obfuscation, like code overlapping, self-modification, and things like this. So in comparison to static and dynamic, it's robust and correct thanks to dynamic aspects, and it's more complete because it allows to generate new paths. The main shortcomings of these methods is that it has some scalability issues, because when you obtain some strong relation on the path, they might be really difficult to solve, and that makes it really difficult to scale then. Okay, so we have dynamic symbolic execution. It allows us to find new targets for dynamic jumps, to cover new branches, and so on. But what if instead we want to check some infeasibility properties, like we want to make sure that a ret instruction is always going to return to the call instructions? Or another example, for opaque predicates, we want to check that we are always going to take one of the two branches. So we would like to check the infeasibility of some events. So in the case of opaque predicates, it would be the infeasibility of going into one of the two branches. So there is a problem. The standard forward DSE is not really adapted for such problem. And that's why we propose a new approach, which is the backward bounded DSE. So it's a complementary approach to forward DSE. So the basic idea is that you have, for instance, here a conditional jump, and you would like to check that we cannot take, for instance, one of the two branches. So you're going to execute it symbolically in a backward manner. If you don't go back enough, you will not prove it to be infeasible. If you manage, for instance, here to return to the emule, you will prove that you cannot get into the branch. And if you manage to go up to here, for instance, you are complete because you have backtracked on all the dependencies of the registers. Another example is for call stack tampering. So basically, if you have a ret instructions here, you go back to the return to the call by symbolically executing it backward. And you can have a false negative if you don't go back enough. And you can be correct if you find here, there we have the tampering. And you can manage to be complete if you cover all the branches leading to that ret instruction. Okay, so as a summary, the backward bounded DSE is bounded. So the main advantage to this approach is that it scales to whatever execution trust length you're dealing with. And that's important for obfuscation. And it does not solve the same problem that standard DSE, so it's a complementary approach. The point is that here, for instance, if you go back 4 steps backward, from the logical point of view, you're going to over-approximate all the possible paths leading to that location. And moving 1 step further, if you have proved your property by moving 4 steps backward, it will still be infeasible by moving 5 steps. So it's not false negative, neither false positive free, but the rates are quite low. Okay, what about the bound selection? So typically for call stack tampering, we are going to return from the ret to the call. And for opaque predicates, the point is finding the right balance between the false negative you can have and the false positive. And by benchmarking classical opaque predicates that we have found, usually 16 to 20 instruction backward was enough for proving the opacity of predicates. So the idea is to use this algorithm into a combination of dynamic disassembly, static disassembly, and dynamic symbolic execution. And the idea is to compute some obfuscation-related data with symbolic execution and provide it to static disassembly in order to preventing it to disassemble dead branches, telling him to disassemble red targets, and things like this. So the idea is from a safe partial graph, you improve it with static disassembly guided by dynamic symbolic execution. And you can potentially, with dynamic symbolic execution, by the way, generate new inputs for generating new traces and so on. So as an example, here we have a partial graph obtained by running the program. We have handled some targets for dynamic jumps. Because we are doing it dynamically, we can handle some layers of self-modification because we are simply going to execute them. Then we can enlarge the control flow graph with static disassembly, and also preventing the static disassembly to disassemble, for instance, here, a dead branches. If we manage to prove that it's opaque, we can instruct the static disassembly to disassemble red target if they are not returning to the call. And obviously, we can instruct the static disassembly not to disassemble the instruction right after the call if we never return to it. So the basic idea is to obtain some more safe and precise disassembly of the program. Okay, so this combination and these algorithms, we are implementing them into Binsec, which is our platform for binary analysis. It's basically composed of three entities. The main platform, Binsec, which is doing static analysis, symbolic executions, and many other functionalities. We are using a tool called Binsec, which is our dynamic instrumentation, which is basically based on pin. So for now, we only do x86. And the last entity is HIDA-sec, which is HIDA plugin for triggering analysis, recovering the results, and so on. And all these three entities are communicating with message queuing and 0MQ. Okay, so Binsec is based on pin, not the latest versions, but the one before. It can generate, obviously, execution trace in protobuf. It works on Linux Windows. We can configure it with JSON file, for instance, if you'd like to do some on-the-fly value patching or these kind of things. And it keeps tracks of the self-modification layer that we might be executing. Problem is that we don't have all the anti-debug, all the anti-VM countermeasures that might be used by malware for evading such instrumentation. Then Binsec. It basically provides a front end for x86 into our intermediate representation and provides some static analysis, abstract interpretation, and I did implemented the dynamic symbolic execution. So we provide many functionalities for path coverage and so on. And the most critical point on which we have invested most of our time was the path predicate optimization, because in the end, the problem is always the scalability of the formula you are going to generate. So this is the most critical part. You have to generate formulas that are optimized enough to be solvable in a reasonable amount of time. So there's a lot of other dynamic symbolic execution out there, Triton, MIAM, S2E, and basically all the CGC challenger of the DARPA challenge. IDA, it's a plugin for IDA that leverage the results of the analysis into IDA because it provides some nice UI and high-level functionality for manipulating binaries. So we take advantage of this. And it basically, do the post-analysis of the results. Okay, so that's great, but let's move on to the concrete studies. So we selected 33 packers from the wild, and we say, okay, let's try to find if there is some opaque predicates or cold stack tampering into them. So we basically analyzed the 33 of them. We bounded the execution with 10 million instructions, and the goal was basically to perform some kind of fully automated and systematic analysis of the packers to validate our approaches. So this is the results. They are not complete, but this is some of them. That's kind of dense, but what we can quickly see is that, okay, the analysis scale, because we managed to, thanks to the backward bounded DSE, we managed to analyze multi-million trace length path. So the techniques works well. And it basically managed also to find some good matches for opaque predicates and cold stack tampering. And with that amount of values, it's beyond false positive rates. And the last aspect that was surprising is, for instance, some of the packers only have one tampering for the ret instructions. And it appeared that it was packers that were doing the tail transition to the original entry point of the program by doing a push and ret instructions. So obviously the ret instruction is going to be detected as tempered. Okay, what we have found into it. So for instance, in AC products, we found plenty of opaque predicates, and there were basically just chaining to strictly exclusive conditions. So GS, GNS, and we found all the possible alternatives. So GP, GNP, GO, GNO, and so on. Why not? We found in Armadillo XOR ECX, it's obviously going to be 0. So we are always going to take one branch. That's primitive, but still working. Some cold stack tampering into, for instance, AC protect. So this is basically the first instruction of the program. This is push, push, ret, ret. So basically when you disassemble with IDA, it just gives you 4 instructions. So it's not really worth it. Another one that we found also in AC protect. So we perform a call, and then we modify at the top of the stack the value and just return to it. So we are going to jump somewhere else. Another cold stack tampering that we found in ASPAC this time. And the dynamic instrumentation yielded that we did enter into a new self-modification layer. And so you can see the tampering here, push 0 and ret, but dynamically at the execution, at runtime, this instruction, the move, is going to patch the push instructions with the original entry point and then jump into the original program. So that's why we detected that we did enter into a new self-modification layer. Last example is an opaque predicates in ASPAC. So you have move 0 into BL, compare BL to 0, and G and Z. So when I reversed the program and looked into it, I was like, okay, that's an opaque predicate. Our algorithm will manage to find it. But while looking at the results, the result told me, oh, no, it's okay. I've covered the 2 branches. So I was like, okay, there's something wrong with my algorithms. But by looking at the dynamic execution trace, it was kind of the same trick. And it appeared that the inc instructions that is on the right branch is going to patch the opcodes of the move, so that later on, when you come back in the G and Z, you're going to take the other branch. And that's pretty much why it validates the fact that it's interesting to do it in a dynamic symbolic execution rather than purely static, because purely static symbolic execution couldn't have detected such tricks. Okay, so let's move on to the big deal, external. So you've probably heard about this group for the past few months. So they goes by the name of APT28, Fancy Bear, Sofacy, Sednit, Pawnstorm, and so on. They have been targeting lots of entities, NATO, EU, German parliaments, TV5 Monde in France, and recently the Democratic National Committee, DNC. It basically uses lots of 0 days to spread it, to infect the targets. And very recently, I don't know if you've heard about it, this Monday, there was the release of the details by Google of 0 day into Flash and Windows 10 for Sandbox Escape. And it appeared that it was this group that was using it for targeting their targets. So they also use plenty of tools, droppers, downloaders, rootkit, bootkit, and so on. And we are going to give a focus on external. Okay, so the main malware is X-Agent. It's running on the infected machines, and it is going trying to reach the CNC server, the control command server. And if it cannot connect to it directly, it's going to find on the internal network if it can find the external malware to connect to the CNC through it. So external is basically a proxy, a ciphering proxy that is going to encapsulate all the connections into RC4 cipher and encapsulate the whole thing into TLS. And a friend of mine, Joan Calvé, that I would like to thank, have provided me 3 samples of external. The first one is has been compiled in June 2015, if dates are correct. And he provided me also 2 other samples. And the point is the 2 other samples are twice bigger than the original sample, almost. So for instance, the first one is 1.1 megabytes, and the 2 other are 2.1 and 1.8 megabytes. So, and if dates are still correct, they have been compiled, like the second one have been compiled 1 week later, and the other one few months later. So that would be surprising to add that much new functionalities into the program within the small range of time. So just by looking into it, we found lots and lots and lots of opaque predicates. So the first question was, okay, can we remove it? And the answer is yes. So far, it works well. And one of the main questions was, are there new functionality into the obfuscated binaries? Because we would analyze obfuscated binaries if we have not obfuscated one. And the answer for that is that we'd like to know if there is new functionalities into the obfuscated samples. And the answer for that is, I don't know. Okay, but because I've get rid of the obfuscation, this is the next step toward finding if there is new functionality. I'm going to give some insights of either or not there is new functionality into it. So what's the analysis context? So first, we are going to go fully static in opposition to what we have presented before, because it appeared that the malware was not using any self-modification features. So we basically have the whole CFG, even though it's really big. And a good argument is that we don't want to connect to the command and control server, neither to wait for clients to connect on the proxy in order to obtain some relevant executions. So we are going to do it fully static. So first step, we perform our opaque predicate detection with our backward bounded DSC and so on. We will try to recover some high-level predicates, so trying to find what kind of predicates they have used. Then if everything goes right in the 2 first steps, we should be able to remove all the dead code and the spurious instructions. So basically, spurious instructions are instructions that are involved into the opaque predicate computation, but only for that. So if you manage to prove that there is an opaque predicate, you can basically get rid of the instructions that are computing it. And last, if everything goes right up to here, we normally should be able to extract the unobfuscated CFG of the program. Okay, so a few points about the high-level predicate recovery. So the goal is to compute the dependency on the predicates in order to backtrack all the instructions involved in the computation. So on the left, you have an example of an opaque predicates that you have found into external. And on the right, you have the formula generated in SMT. So if you basically backtrack on the two parameters of the compare, you can basically normally recreate the expressions that is being computed. For instance, here it's BV mule and so on. And if you fold the whole thing, you obtain the predicates synthesized by replacing the register with X, Y, Z, and so on. So the idea of this was trying to identify the different patterns that I've used. Okay, what about the results? So the two binaries basically have 30,000 conditional jumps that we all checked. The symbolic execution took 1 hour mostly, and the synthesis also, but I was not, I didn't really optimize it. It was in Python running into IDA. It's kind of, yeah, I could have done better. And so basically the analysis of the two samples took 1 hour and a half, which is okay if you have time or if you want to take for many coffees. Who knows? Okay. So basically half of the conditional jumps are genuine conditional jumps, which are right, which is good. And a significant amount of them are opaque. And among them, we managed to find what are the how many false positive and false negative there were. And the question is, how do we have obtained the false positive and false negative? And this is basically because the synthesis yelled that they only use two different predicates into the program. So the well-known 7 times y squared and so on. And another one that I've never seen elsewhere in other obfuscators, which might be good for doing some signatures, or I don't know. And using these two patterns, I've been able to identify among the results which predicates were false positive and which one were false negative. And we basically missed really few of them. Okay, then I tried to find what was the basic distributions of the obfuscation within the functions. And it appeared that most of the functions are not obfuscated at all. So 3,000 of them are not obfuscated. And by looking at them, it was basically the functions of the statically linked libraries that were embedded into the program. They are using OpenSSL and so on, and all these functions are not obfuscated. Why not? But it allows us to narrow the analysis on the obfuscated sample. So we only have like 500 functions remaining. So that's a lot, but that's better than 3,000 of them. The code coverage. So we started from 500,000 instruction. By propagating the liveness of instructions, we obtained 200,000 of them that were still alive. And when you remove the dead instruction and spurious instructions, you obtain basically a difference with the unobfuscated sample, which is for the sample one, 47,000 instruction. And for the second sample is 9,000 instructions. So that's actually really low. It could have been noise that remains from our analysis that could have missed some spurious instruction and so on. So with these results, we are kind of not optimistic about the fact that there is really new functionalities in the obfuscated samples. So basically you have the control flow graph of a function. I took the first one I've found. When you perform the analysis, you are able to to flag the basic blocks if they are alive, dead, and so on. And this allows you to extract from it the unobfuscated control flow graph. Okay, so I'm going to do a quick demo. So I'm going to run Binsec as a server. So it runs locally on my machine. And then I'm going to launch HIDA. So this is external. This is one of the first function is the start function. It's kind of big, but not that much. I'm loading HIDASec, our plugin. I'm going to connect to Binsec locally. So here we are connected. And I'm going to trigger the analysis I've developed for these samples. It's the static opaque, so an opaque predicate analysis, but statically. We set the bound to 16. It should be enough for most of them. And I'm going only to analyze this routine. Okay, so this basically generates JSON configuration file that is going to be sent to Binsec, along with all the subpaths of the conditional jumps of the functions. And it should be okay. So we start. There is 45 conditional jumps in the functions, so we process them all. And here it is. So among the 45 conditional jumps, there is only 2 of them that were genuine, and 43 of the others were opaque predicates. And we can double check it by looking at the predicates that have been synthesized. And as you can see, it's always the same kind of. Sometimes we did not manage to replace the register by a placeholder, but we can basically see that they are all the same predicates. And among them, there was only 2 that were not opaque. So at the top of that, I've implemented like fancy functionalities for highlighting in the control flow graph what is dead, what is alive, so that tells us to quickly see what's of interest. I can also highlight the spurious instructions. Here you can see that all these instructions are just calculating the opaque predicates. So if you remove it, you can basically have the payload. And at the top of that, we can have, thanks to HIDA API, I've done some extractions to a reduced CFG. And here it is. So this is basically the function without all the spurious instruction and dead code, which is more visible and usable for further analysis. Okay, so let's back to the. Okay, so what are the conclusions about external? So manual checking of extracted CFG with the original functions of the first samples didn't yield really significant differences or any new functionalities, but that would really require more in-depth graph similarity like BinDiff or so on for trying to find if among these 500 remaining functions we can find something of interest. The obfuscation itself is not really, it was quite of great because they managed to create some for dependencies between the instantiation of variables and their usage into the predicates. So the depth might be quite big. And also they do some code reuse, code sharing between the predicates. So all the predicates that are not standalone. They are relying on each other for computing some parts and so on. So it's a kind of code sharing and dependency with each other. And I would highly, if you want to have more information about the external, X-agent and so on, I highly recommend the presentation Visiting the Bearden by Joan Calvet, Jesse Campos, and Thomas Dupuis which has been presented at Recon, but is going to be presented at BotConf this year. Okay, what about the takeaways of Binsec? So this is definitely the tip of what can be done with Binsec. I've only shown what we can do with dynamic symbolic execution, but Binsec also allows to do abstract interpretation, simulations. It has some optimization and really interesting things. So more is yet to come. The platform is really young. It lacks of documentation, stabilized APIs, but it's coming. But still, you can download it, try it, and experiment with it. If you have any questions, just ask. We are available. And the main takeaways of the talk is backward bounded DSU scales well, and we have managed to show it on packers that are kind of huge in terms of execution trace length. The backward bounded DSU yield really good results on external because we managed to get rid of the obfuscation. And we definitely think that combining dynamic, static, and symbolic analysis and approaches is definitely the way to go on obfuscated binaries in order to handle the different kind of obfuscation we can meet into this program. And that's all for me. Thank you. If you have any questions, I'll be happy to answer. Yeah.
And you're in essence deciding how far to go back.
Yep.
You talked about 16 to 20 as being suitable for
yep.
a lot of things. I'm assuming you just did that by trying a whole load of values on a whole load of code.
Yeah. Even though, for instance, on external, even though sometimes they have some for dependency, we managed to recover enough constraints on the inputs so that we can prove the opacity of the predicate. So you don't need to backtrack all the dependency, but by backtrack for the example of opaque predicates, if you backtrack enough to recover enough constraints on the variables, you will be able to prove the infeasibility.
Based on how far you got,
yeah.
Surely you can't know that there's not something before that.
Yeah, we basically, for your question, tried multiple bound for this problem and found out that 16 to 20 was kind of great. Yeah, it was the best balance between false negative and false positive because there is still some false positive or false negative. Okay.
What if the program uses some sort of parallelism like threads and dependencies among them?
Oh, okay. The question was if we're the malware was in parallelization, and the answer for that is you should normally execute symbolically all the threads separately, and yeah, it's kind of difficult to model that the interactions in memory that can have. Yeah, that's kind of complicated. We basically don't do it for now. Okay, so if there is no questions, oh yeah.
Well, you're patterning, sort of like dependencies between these branches.
Yeah.
So how would that handle backtracking? Because there are some simple logic, but it begins like a couple loops ago.
Yeah.
And does do anything to it or?
I've not looked into the CFG flattening obfuscation, but yeah, that would be a great deal to try to find the right bound and for dealing with it. But I'm not really sure that if for these specific cases, using it backward is really valuable. I don't know.
Because it's not really opaque, right? It's pretty blunt, but it just needs to go back a
Mm,
Like, okay, you start with x is 5, and in each branch you add 7 to it, for example, and something. And then
oh yeah, sure.
you do switch based on the value.
Yeah. So that's why we still have some false positive and false negative. Sometimes just because we took the wrong branch, we'll falsely believe that this is an opaque predicate, while we could have come from somewhere else. I don't know if that's replying your questions. Okay, so thank you all.